students, welcome to the chemistry sessions. So I hope you all have revised what we have done in the last session. So what did we do in the last session? We discussed about, we started with the water, yes, I had given you an idea, and before that we were discussing about the hydrides. I hope everybody remembers that. And let me just ask you a question over here I have got for you is about pH 5, right? Does it exist or not? This is the hydride, yes? Is it capable of existing or not? Tell me. So basically the answer lies, and the answer is no, it is not. It is unstable. Why? Because hydrogen, again being smaller in size, there will not be an effective bonding between P and H over here. P getting involved with 3p orbital. But if I talk about the hydride, which is supposed to be here, involves s orbital and that too 1s. So there is so much of energy gap between the two, so the overlapping will not be that effective, and yes, that is why it is not capable of existing. Clear? So that was one question which I wanted to discuss. Now we were talking about the water. Let's move on to this. Water, we discussed about its structure, how it is polar, tell me. So it has got a bent structure, right? It has got a bent structure, it's delta positive because it will be attracting, this oxygen will be attracting these electrons towards itself. It's angle 104.5, right? And this is delta positive, this will be delta negative, delta positive, delta negative. All in total I can say 2 delta negative is the charge over here. Clear? Okay, so that was something about the polarity. Now we went on to the discussion of the ice. Yes, another form of water, the crystalline form of water known as ice, right? Now this ice, again, what is the density of ice? If we say, if we have observed, you must have observed that ice always floats on water. Why is that so? Because of its density. Density is less than water, right? That is why it floats, right? And in fact, this floating property of ice, you must have seen those frozen lakes, right? You must have seen those frozen ponds. So in those lakes and ponds, there are some aquatic life. There is some aquatic life going on, be it aquatic marine animals, be it aquatic plants. So that ice layer which is formed over the lake in very cold regions, right, at very cold temperatures, that acts as an insulating material for the aquatic life which is below it, which is underwater, right. So that is again a very good property of it, its insulating property, right. Clear about it? Okay, so that was something about ice, and let's draw its structure then. Now you must have seen a 3D kind of a structure in your books, right? Again, we are not going to do that because again it's a very difficult one. We will be defining its 2D one. We will be discussing its 2D structure right here, which is more simpler to form, right? So basically it's a 3D network, right? Let me just write the specifications over here for you. It's a 3D network, right? It has got hexagonal rings. And you know what exists in this ice? It's the H bonds, right? And let's draw its structure then. I told you that I have got the hexagonal rings, right, with alternations of oxygens and hydrogens. So first of all, try to draw a hexagon, right? And what I am drawing over here is the oxygens which I need. In between the oxygens you will be putting H, right? Let's put hydrogens then. Fine. Now this oxygen connected with 2. Again there will be a hydrogen connected. Again there will be an oxygen connected. Let's draw one more hexagonal ring then, right? Hydrogens connected. So all of these are via hydrogen bonding we have got, right? That is how it goes. From the oxygens you have to show the bonds, right? So these are further the H bonds. And that is what the 3D appearance for the structure of ice is, right? So that is what the 3D appearance is. If we try to complete it over here, right? You can do these simple alternations we have made. Clear? So that is what the 2D representation, and this 2D representation, in fact, an oxygen is bonded with 4 hydrogens over here, making it a 3D network, right? Just like in the case of a structure of diamond, a similar kind of structure is formed over here. Oxygen is bonded with 4 hydrogens, again hydrogen bond getting involved, right? And making it a very rigid structure. Clear? Okay, so that is ice. I hope that is clear to you. Now let's move on to the chemical properties of water, which are very, very important. Okay, so let's move on to the chemical properties of water. Water and its chemical properties. Chemical reactions, in fact, we will be dealing. You know, what is the very prominent, very interesting property of water? That it can behave as an acid as well as the base, right? So that is what a very good property of water is. So first of all, we will be dealing with the amphoteric nature. Amphoteric nature of water, right? We will be dealing with how it is participating in the redox reactions, right? Getting reduced as well as getting oxidized. We will be dealing with how the hydrolysis is done, right? We will be dealing with how the hydrates are made, right? So these 4 things we will be covering. First of all, the amphoteric nature, let's discuss that. So as I told you that water acts as a base as well as an acid, yes? So first of all, in amphoteric nature, it is acting as an acid and it is acting as a base. So whenever it acts as an acid, let me just try to react it with a base. So I am taking up here is ammonia. What do we get? We get is OH negative plus NH4 positive, right? So it is acting as an acid. So if I say that this is acid, this is its conjugate base. If I say that this is a base, it is its conjugate acid. So that is conjugate acid, this is conjugate base, this one is trying to act as a base. Clear? Okay. Now if I move on to that how it can behave as a base. So I must make it react with an acid, right? So in that category, I am taking up the hydrogen sulfide. So basically it's gaseous, we have taken that in the solution form, right? What is going to happen in this case? So again, there will be the reaction and we get here is both of them in aqueous forms, right? You can mention very well aqueous, aqueous and aqueous. Clear? Okay. So here it was acting as a base. We get is the conjugate acid for that. Here we get this is an acid, again giving us a conjugate base. Clear? Okay. So these are the 2 reactions which show over here that it is an acid. It is an acid and here it is a base. Clear? Now here is another property that water again it itself undergoes autoprotolysis, right? So self ionization. also known as autoprotolysis. What is it? See, water self-ionizes itself. Two water molecules, one behaving as an acid and one behaving as a base. This is a very interesting reaction. Mark this as important. So, over here, one molecule will be acting as a base, right? So, what happens? H3O positive, fine, along with OH negative. Clear? So, which one is acting as an acid? See here, if I assume that this is acting as an acid, right? So, it must be generating a conjugate base, right? What is the conjugate base over here? This is the conjugate base. If I say that this is acting as a base, so definitely this is going to be its conjugate acid. And you know that in water I have got hydronium ions and OH negative ions going here and there, right? So, that is why we call this property as self-ionization or autoprotolysis. Clear? Okay. So, yeah, that completes my amphoteric nature of water. That was important one. Now, if I deal with the redox reactions, let's move on to the redox one. Redox nature. Now, in order to show the redox nature, I need is the reaction where we can prove that it is getting reduced and where we can prove it is getting oxidized, right? So, in that category, I have got Na, H2O. What do we get is NaOH plus H2, right? Now, see here, what is happening? It is getting what? Reduced over here. Reduced, right? So, basically here the reduction of water is happening. See here what an interesting reaction this is. This reaction is basically exothermic. Why is this so? Can you tell me? It's due to the release of the hydrogen gas. Exothermic and explosive. Now, this particular reaction gives us a reason that whenever we put sodium in water, it catches fire because of the production of the hydrogen gas. Hydrogen gas, when it interacts with the air, there are explosions, there are fires happening, right? It starts burning actually. So, that is what the reason behind this is, that sodium is so reactive with the water and it catches fire. In fact, the potassium also behaves the same way. Clear? Okay, here it is getting reduced, so it's a reduction reaction basically. Basically, it's a redox reaction if you see here. Na, earlier it was 0, now it has become 1, right? So, it's a redox reaction. We are only concerned with the water which is getting reduced over here, right? Now, if we talk about that what all reactions are there where the water gets oxidized, I have got such a prominent example, that is the photosynthesis which happens every minute, every second it's happening. What is this? Photosynthesis. In photosynthesis which is done in the plants, it's actually the water they take and the carbon dioxide from the atmosphere. So, 6 CO2 plus 12 H2O giving formation of glucose in the presence of sunlight we are dealing with, right? And we get is C6H12O6, that is the glucose formed, plus 6O2 plus 6H2O. What do you get over here? It is getting oxidized, right? The water is getting oxidized over here. Clear? So, there is an oxidation process. So, I hope everybody is clear with the fact. So, we are through with the redox nature as well. So, these are some of the redox reactions which it performs. Now, come up the hydrolysis, right? Okay. Now, the question number 1 to 3 will be 1 mark. So, just answer accordingly. What is the trade name of hydrogen peroxide used as an antiseptic? Now, that's an important question. So, we know that hydrogen peroxide is used as an antiseptic, and what is the name for the compound basically? That is perhydrol. That is the compound. You must learn this. This one is important, and it is used as an antiseptic, that too a mild antiseptic. Mild antiseptic. Fine, clear? Let's move on further then. Okay, so the next question say, which isotope of hydrogen, so we have covered up this particular topic as well, that what all are isotopes of hydrogen, fine. Okay, so we have got 3 isotopes, so one is protium, right? Another one is deuterium, third one is tritium, right? So this is protium, deuterium, tritium, and this protium is actually H, nothing but the hydrogen we call it, fine. And they are asking does not contain, which of them does not contain any neutron? See here, if one is electron, so one must be the proton, then the neutron will be over here 0, right? Over here neutron 1, over here neutron 2, clear? And I know my answer, that is protium, right? So don't just write hydrogen but write protium, it would be appropriate. Which one is radioactive? So you know it's the tritium, right? Clear? Okay. So let's move on further then. Question number 3. Arrange. Now this one is important. Arrange H2, D2 and T2 in the decreasing order of their right. So I need is the arrangement of these 3 isotopes, right, in the boiling point. So as I have told you that higher the mass, bigger the compound is, that means more the mass, more will be the boiling point. We know this, right? So which one will be having the most boiling, most mass, more mass? That will be tritium, T2, then D2 and then finally H2. That is my possible order for the boiling point, more mass, see here, more molecular mass, more boiling point, right? So this particular rule is also followed in the case of hydrocarbons. More the mass of the hydrocarbon, more will be the boiling point, because more is the van der Waals forces of attraction. Heat of fusion or enthalpy of fusion. Enthalpy of fusion, what does it mean? Fusion means it's basically the dissociation of the compound, fine. And we know that heat of fusion will be highest in the one having more mass, right? So again, this would be my decreasing order, right? So done, clear with the fact? Now let's move on to question number 4 then. Question 4. Now it's of 2 marks. Name the classes of hydrides. So first of all, what I would like to tell you over here, hydride topic is very important. Question can arise from this, fine. Name the classes of hydride to which these 4 belong, right? So they have given certain compounds, we need to classify, we need to differentiate in between the different type of hydrides. So we have learned 3 types of, one is the ionic, next is covalent, and the next is interstitial, or also known as non-stoichiometric. Yes, remember this? Covalent or molecular, ionic or saline. Clear? Okay. Now let us just classify these 4. 1. H2O. See here. So first of all, this is a covalent compound, fine, you know this, and it's a covalent hydride. To be very precise, the 3 types of covalent hydrides are electron deficient, yes, electron precise, that means exact number of electrons, not more, not less, just the perfect, electron rich, right? Now out of the 3, which one is this? It's electron rich, it has got lone pairs. So it's a covalent molecule, a covalent or a molecular hydride with electron rich component, fine. It's a type of electron rich covalent hydride, you can say, B2H6, again it's an hydride, but that too, okay. So the bonds over here are covalent, so you get to know that this is covalent molecule, covalent hydride. And this boron is electron deficient, right? And we get to know that this one is included under the category of electron deficient. If I talk about NaH, see here, so it's not covalent, it's basically ionic compound, Na plus and H negative it is. So it's included in the category of ionic or saline hydride, fine. And also S block elements usually form ionic hydrides. You must remember this, and that is why I have chosen this as my ionic hydride. If I talk about TiH2 now, this one is good one. TiH2, so some of the very specific examples must have been mentioned in your books as well, and I have also told you that this will be included in interstitial or non-stoichiometric hydrides, fine. First of all, just try to recognize that this is belonging to D block element, right? And this gives us an idea that yes, it would be an interstitial. To be very precise, TiH2 is given. So basically it's not TiH2, but it has got a little deficiency of hydrogen hydride, which is approximately, it's 1.5 to 1.8, not exactly 2. Clear? Yeah. So this belongs to DNF. This belongs to what? P block. This belongs to S block. Clear? Okay. So done with this. This was a very good, interesting question it was. Now comes up the next question. Now, it's a very good question. See here. Rohan heard that instructions were given to the laboratory attendant to store a particular chemical. So they are trying to find out some particular chemical. Particular chemical, that is, what were the instructions given to the laboratory attendant? Keep it in the dark room, add some urea into it and keep it away from the dust. This chemical acts as an oxidizing as well as reducing agent in both acidic and alkaline media. Have you got the compound? What is it? See here, it acts as an oxidizing as well as reducing. We have done this in acidic and alkaline media, and this chemical is important for use in the pollution control treatment also. What is it? So it's a very familiar kind of a compound we have did. Hydrogen peroxide it is. See here. So as I've told you, we have to keep it in dark, because again what happens is, let's first of all read the question. Name the compound. It's the hydrogen peroxide, we know this. Explain why such precautions are taken. So the precautions, first of all, dark room, because it easily dissociates in the presence of sunlight, right, giving H2O plus O2, and in order to prevent it from dissociation, we keep it in dark, right. Add some urea into it. Why? Again, it prevents the decomposition of it, fine. Urea is actually acting as a stabilizer into it, right. So urea stabilizes it. And if I talk about the dust, if there is dust, the presence of dust can be very explosive. It will dissociate, it will decompose in the presence of dust explosively, right. So that is why we have to keep it away from the dust in a properly closed container. And that is what the question is. I hope that is clear to you. Okay. So that is it. That was question number 5, and an interesting one. Now, write the chemical reactions to show the amphoteric nature of the water. You have to find out the amphoteric nature. That means water is behaving as an acid as well as a base, right. So see here, water. First of all, if I am trying to show that this particular is behaving as an acid, then we have to react it with a base, right, and that is, I have chosen ammonia in this case. I get is NH4 positive plus H plus. Since this is giving H positive, see here in the equation, that is why it's acidic. If I talk about that it behaves as a base, so I am going to react it with a species so that it leads to the formation of something, right. What is that? So it's basically SH negative plus, what is left? Yes, is it? So I hope everybody has got it, that I am left with OH negative over here, thereby making this as a base. Yes? Clear about the fact? So that was, yeah. Okay, wait for a moment. Oh, wait for a second. What I have done over here is see this particular reaction carefully. Whenever NH3 is fetching one oxygen, we get OH negative here, see. Right? The correct equation is this. Now, if I talk about here, now that is why I was getting confused over here. You must get H3O positive plus SH negative. Now it's perfectly correct. And yes, with that matter of fact, it changes. Yeah. So it shows these two both reactions shows its amphoteric nature. Clear? So I hope that is clear to you. That is acting as a base, that is acting as an acid, that is acting as a base, that is acting as an acid. Clear? Okay. Now let's move on further then. Yeah. Question number 7 to 9 now, 3 mark questions. Calculate the volume strength. Now this one is important. And yes, so we are going to solve it together here only. Calculate the volume strength of 3% solution of H2O2. Now I need to find out the volume strength. That means volume taken for 3% solution of H2O2, right? Volume strength means I need to calculate the volume per, strength means per liter of the solution actually, right? Volume specifically I am talking about for what? Let's see here. So basically 3% solution of H2O2 means 3 grams, right, will be dissolved in 100 ml of solution. And now we are talking about the 1000 ml. So 30 grams will be dissolved in 1000 ml per liter I have calculated. Fine. Now if I talk about the reaction, see here, the reaction basically is the formation of oxygen, right? Fine. Balancing it out, right? So here what is the molar mass of H2O2? We know this, it's 34 into 2 will be giving how much of oxygen? See, it's 1 liter, 1 mole, fine. And that too, 1 mole will be corresponding to, if I talk about at NTP, right? It's 22.4 liters, fine. So basically 68 grams will be corresponding to 22.4 liters, fine. See here, so 30 grams will be corresponding to how much, right? Let's find out. 30 grams will be corresponding to 22.4 liters by 68 into 30. Now what do we get over here is, we get 9.88 liters, fine, approximate value, and that is per liter of the solution. Now if I talk about in ml, right, so that was when 1 liter was giving, that means 1000 ml of solution was giving 9.88 liters, fine. So that means if I talk about 1 ml will be giving 9880, this will be in ml, fine.